Namaste students, welcome back to Rama Teaches You. Today we are going to do the IB Physics textbook T3 Force in Electric and Magnetic Fields. Okay, Motion in Electric and Magnetic Fields. Okay, that's the name of the chapter, right? Okay, Motion in Electromagnetic Fields. Now, in the last video, this is the second video. The last video, what we did, in the last video, we made sure to understand how a force exists in a conductor, right? Mu naught Ni by 2 pi r. Okay, that was the force that existed in a single conductor. That was the electric field that existed in a single conductor, and by using two conductors, we were able to understand how much force exists between these two conductors, right? How much force exists between these two conductors. Now, what was the logic behind it? The logic behind it was, if you have a current carrying conductor placed in a magnetic field, it will experience a force which will allow the conductor to move, and this is also known as the motor rule, and we can find the direction of force by using the Fleming's left hand rule. Okay, Fleming's left hand rule can be used to understand the force that exists between these two conductors. Okay, that's what we learned yesterday, and the formula for the force that existed between the two conductors is given as mu naught I1 I2 L upon 2 pi r. Okay, but more importantly, instead of finding the force, it is advantageous for us to find the force per unit length. Okay, force per unit length is a much important measurable quantity in force, okay, than force. Now, the formula for that is what? F upon L is equal to mu naught I1 I2 upon 2 pi r. Okay, that's the formula that we get, force per unit length. Okay, what is the value of mu? What is mu naught? Mu naught is the current. Sorry, mu naught is the permeability. Permeability that, okay, that exists in vacuum or free space. Then what is I1? I1 is the current in the first conductor. See, basically what you do, you find the magnetic field produced by the first conductor. Okay, and you see how this magnetic field affects the other conductor by using the formula of, exactly, by using the formula of BIL. Okay, BIL sine theta can be used to find the force that exists in the other. And similarly, these two, there will be a reactionary force due to the conductor 2 on conductor 1, because it follows the Newton's third law. Every action has an equal and opposite reaction. Every force will have an equal and opposite force on the other object. Okay, so that's where we were in the previous class. In this class, we are going to continue with this, most probably finish this chapter. The equation B is equal to mu naught I upon 2 pi r is the version of Ampere's law, named after the French physicist André-Marie Ampere. Ampere's father was a wealthy merchant who took a great interest in his son's education but did not believe in formal schooling. As a result, André-Marie Ampere was largely self-taught using his father's library. One of the few areas where Ampere received formal tuition was Latin, which enabled him to read some of the academic texts in the library. Ampere went on to make many discoveries in what he called the electrodynamics. Okay, what is electrodynamics? Electrodynamics is a phenomenon in which a charge starts to move. That is what electrodynamics means. Okay, electrostatics is what? When a charge is stationary, we use the field electrostatics. Okay, when the charge starts to move, we call it electrodynamics. Okay, so basically there is a whole section called electrodynamics. There are books called electrodynamics. This is not a single section in a small chapter. This is a whole study that we have to do. Okay, now let's move on. So and the SI unit, the most, we still know Ampere because his name has been used as the quantity for current. Exactly, exactly. Another scientist who researched the magnetic fields caused by electric currents was the British physicist Michael Faraday. Faraday was also largely self-taught. However, his family was not rich. Faraday became an apprentice to a bookbinder, and it was by reading some of these books that Faraday was able to start learning about electricity. See, why are they telling you these things? Huh? What is the point of this? Why not just focus on their work and not on their scientists? Why are we focusing on these scientists? We are focusing on these scientists is because these scientists, without formal education, taught themselves how to read and write. Not just that, they taught themselves how to read and write. They taught themselves these fields, and not only that, they contributed to the fields also, right? Basically, so even if you can't go to school, even if you can't do, if you have the hunger for learning, nobody can stop you. Understood? Now, while Ampere's research uh, while Ampere's research was largely theoretical, Faraday was a gifted experimentalist. Who is an experimentalist and who is a theorist? A theorist is a person who comes with different theories. Okay. Experimentalist is the person who actually uses those theories and makes sure that whether they are an actual experiment or not. Right? Huh? If they can be correct or not. There are two fields, like basically a theorist and an experimentalist. Okay. Okay. Now, how can independent research augment your own studies? Of course, it basically has no bound. There is no person limiting you from not reaching your full complete potential. I taught myself a lot of theories. Right now, currently, I am a PCM student. That is, in my 11th and 12th, I took physics, chemistry, and maths. But I have a dream of teaching bio in the future. I have a dream of teaching commerce in the future. So I have already started basically, aggregating all the books so that I can teach myself these concepts. So that in the future, I'll be able to not only teach science students, but also commerce students also. Okay, so there is no bound, like you can only learn this much, or you only have the ability to learn this much. Understood? Let's move on. I think I went through a tangent, but it's an important lesson for you people. Okay, now electric current of 8 amps and 3 amps are established in two long parallel wires X and Y. The magnetic force of a length of 0.2 meter wire X due to a current in wire Y has a magnitude of 1.5 into 10 to the power minus 5 newtons. Let's actually uncover what is happening here. Okay, what have they said? They have said that electric current of 8 ampere and 3 amperes are established on two parallel wires X and Y. So X is carrying 8 amperes. Yeah, I1 and I2 we know. The magnetic force on the length of 2 meter of wire, 2 meter of wire X due to the current in Y, the current in Y. So basically we have to find the magnetic field produced by the current one, and we have to use that magnetic field and how it affects a force on current Y. Okay, so has a magnitude of 1.5 into 10 to the power 5 minus 5 newtons. Due to the magnitude of magnetic field on a length of 0.2 deduce the magnitude of the magnetic field or magnetic force on a length of a 0.2 meter wire Y due to the current X. Okay. Uh, they will both be the same. They will both be the same. Yeah. Why will they both be the same? I just told you they will be the same because of Newton's third law. If X is putting a if X is putting X is putting a force on Y equal to 1.5 into 10 to the power minus 5 newtons, then Y will also put a force on X of the same magnitude. Just the direction will be different. Just the direction will be different in the opposite direction. Exactly. Now, because students will no, they won't trick you. See, if a student's theoretical knowledge is not high enough, he will start calculating for it. They will be making him waste his time. If he doesn't know that the magnitudes are the same but in the opposite direction, he will calculate them. He will also reach to the same conclusion that the force is 1.5 into 10 raised to power minus 5 newtons, but he would have wasted his time, which he doesn't need to, which he can avoid. Understood? Now, Akshay, from yesterday's learnings, what type of force acts between two conductors where the current is in the same direction? Do they attract or repel? When the two currents are flowing in the same direction, when the two currents are flowing in the same direction in two conductors placed parallelly next to each other, will the force be attractive or repulsive? Attractive force, and when they are in the opposite direction they become repulsive in nature. Understood? Okay, calculate the distance between the wires. We have to calculate the distance between the wires. So we know that force is equal to mu naught I1 I2 upon 2 pi r. Then you had L also, right? And we know the force 1.5 into 10 raised power minus 5 newtons. Okay, now all we have to do is to find the value of L. What do we need? See, F upon L, as L would be F upon your this thing. Mm, wait. R is equal to mu naught I1 I2 into L upon 2 pi F. That will be the answer. Understood? Exactly. Clear? R is the distance between the wire. L is the length of the conductor. BIL sin theta. Remember how we got this formula? We got this formula using BIL sin theta. Okay. And what is L in that BIL sin theta? That L is the length of the conductor. Exactly. Understood? Yeah. So if you deduce this formula, put the values in the calculator, you will get 6.4 centimeters. Clear? 6.4 into 10 to the power minus 2 meters is what you will get, but you can call it 6.4 centimeters. Let's move on. Now, the whole of theme D involves physics based around inverse square law, right? That's what we did in gravitation. That's what we did in electric force, electric field, acceleration due to gravity. All of them followed the inverse square law, where the force decreases to the second power of r. Okay, so basically, Ampere's law features a 1 upon R law. The database question on page 535 features an example of a 1 upon R cube law. Why are these different? The inverse square law applies to a single point source. This could be of radiation, charge, mass, etc. Okay, it can be thought of as a consequence of a sphere, sorry, a consequence of field lines spreading out in three dimensions over the surface of a sphere, which increases in the area as a is directly proportional to r square. So basically, the r square logic always applies when we have spherical objects. Okay, when the field is spherical. For example, the gravitational field produced by the earth is spherical in nature. Okay, similarly, the field produced due to a stationary charge is also spherical in nature. Right? That's where the r square, 1 upon r square logic comes from. Okay, r square suggests area. Okay, so area is what matters. Understood? Area is directly proportional to r square. Ampere's law involves a long wire. You can only move away from it in two dimensions rather than three dimensions. Okay, because see, in a point charge, you could move. Like, for example, if this is a point charge, I can move like this, I can move like this, I can move like this, and I can even go on top of it because it's a point charge. This is a single point charge. Understood? Okay, but if I have a wire like this, I can only move in two dimensions. I cannot move in three dimensions with respect to this wire. Okay, let's move on. Now, the electric field around a straight, yeah, around a straight charged wire could have similar 1 upon r dependence because the field lines cannot spread out over the three dimensions, the length of the wire. Okay, what about an infinite two-dimensional sheet? You have already seen this situation. This is the same as moving away from the surface of the earth, not so far as to observe the earth's curvature though. In this case of the two-dimensional object, the field lines are unable to spread out at all. The field is uniform and does not decrease with distance. Okay, the field does not decrease with distance when you have a square or a flat surface that is producing the field. Okay, when you have a flat surface producing the field, the field, because of its uniformity, it does not decrease with distance. Okay. Okay, now the database questions of page 535 is a different case. A magnet has two poles, North Pole and South Pole, and so we are not dealing with a point source. If the North and the South Pole were placed one on top of each other, they would cancel each other out and there would be no field at all. However, the two poles are displaced slightly, so you might experience a field by being fractionally closer to one pole than the other. This is called a dipole effect. Okay, what is a dipole? A dipole is basically when there are two poles, when there are two alternate ends. When there are two alternate ends separated by a certain distance. For example, you can have electrical dipole also, like where you have a positive charge and a negative charge placed a certain distance away from each other, both of them having the same magnitude of charge. Okay, if they are having the same magnitude of charge, you call it an electric dipole. Any bar magnet you see is a magnetic dipole. Why? Because there are two poles in the magnetic field which are separated by a distance equal to the length of the magnet. Okay, that is known as a magnetic dipole. Okay, this is called the dipole effect. Now, some practical questions. Three long parallel wires P, Q, and R are separated by a distance of 1 meter, 0.1 meter, and carry equal currents of 5 amps in the same direction. Okay, calculate the magnetic force per minute of wire length on calculate the magnetic force per meter of wire length on wire P. Okay. On P, there will be two fields. Okay. On P, there will be two fields. One due to this wire Q. Okay. Look at this. The field is, we are using the right hand. Okay. And this is my right hand. Okay. I'm placing my thumb like this. Okay. And I'm trying to curl my fingers. Can you see it? I'm placing my thumb on this wire Q and I'm curling this finger. So the magnetic field lines produced on this wire are perpendicular to it. Okay, they are perpendicular to it. Similarly, for the wire R, the magnetic field produced by the wire on this wire P is also perpendicular in direction. Okay. So why am I saying this? I'm saying this because the wire P will not only experience the field due to Q, it will also experience a field due to R. So these two fields have to be added up first. And then you use that information to find the force that is acting on it. Since both the fields are acting in the same direction, they will add up together. Okay, now let's actually see what is happening here. We know that the field due to a straight conductor is what? The field due to a straight conductor carrying current is mu naught I upon 2 pi r, right? Huh? Is this correct? Once again. Yeah, it's correct only. Mu naught I upon 2 pi r. Yeah. Okay, so mu naught I upon 2 pi r. Now we know this is what magnetic field is. Now let's use this formula for the wire Q. For the wire Q, what is going to happen? For this wire Q, the distance is 0.1 meters. So I know that mu naught magnetic field due to Q is equal to mu naught I upon 2 pi r of Q. Okay. Now, B of R is equal to mu naught I upon 2 pi, the distance of R from P. So if we want to add these two magnetic fields, what do we do? B net is equal to B1 plus B2 is equal to, what do you get? Mu naught I upon 2 pi 1 upon R1 plus 1 upon R2, because the mu naught I upon 2 pi was same in both of them. All I had to do was 1 upon R1 plus 1 upon R2, right? So let's actually put on the values. What do we get? So mu naught, what is the value of mu naught? 4 pi into 10 to the power minus 7 multiplied by 5 upon 2 pi into 1 upon R1 is how much? 0.1 plus 1 upon again 0.2. Okay. See, it was 0.1 meters away from this one, and this is 0.2 meters away. Right, this is 0.1 meters away and this is 0.2 meters away. So what happens? You will basically get 4, I can cancel these two out and we leave 2 here. 2 into 10 to the power minus 7 into 5 into, this can be written as 10 upon 1 plus 10 upon 2. So 5, 5 plus 10 is how much? It is 0.2 because this wire R is at a distance of 0.2 from this one. No, because see, the both Q and R are producing the same magnetic field. Okay, but the magnitude is different because the distance is increasing. Okay, so what do I get? 15 to the 30, 3 5s are 150 into 10 to the power of minus 7 Tesla. Yeah, 1.5 into 10 to the power of minus 5 Tesla. Okay, this is the net magnetic field that is acting on our wire. Okay, the net magnetic field that is acting on wire Q. Okay, understood? Any doubt in any of the lines? Wire P. For the wire P, due to this, what is happening? Basically, this field of Q and this field of R is both getting added up here. Okay, so that's all we did. Okay, next. Now there is a current that is flowing here, that is 5 ampere current. Now let's use the left hand rule. The current is like this, okay, and the magnetic field is like this. So what will happen? The force will be acting downwards. The wire P will be forced to move downwards. See, middle finger, direction of current. Magnetic field is literally coming outwards, right? Magnetic field is coming outwards. So the force, this thumb, will be acting in the downward direction. Okay, this is how you do it. So the wire, what will be the net force acting on this cable then? We know that force is equal to force per unit, force is equal to BIL. Therefore, force per unit length is equal to B multiplied by I is equal to, what is B? B is 1.5 into 10 to the power minus 5 multiplied by 5 is equal to 15 5 is 75, that is 7.5, sorry, 7.5 multiplied by 10 to the power minus 5 newtons per meter. Okay, that's how the formula goes. Clear? 7.5 into 10 raised to power minus 5 newtons per meter. Clear? Clear na? Okay, let's move on. And the overall force will be downwards. Okay. Next, on wire Q. Wire Q is a totally different story. Look at this. Wire P is producing a magnetic field on wire Q that is coming outward like this. It is coming out. Okay. And wire R is placing a magnetic field inside. Both the magnetic fields are having the same magnitude. Okay. Both the magnetic fields are having the same magnitude. Due to which what happens? Due to which the two magnetic fields cancel each other out. There is no net magnetic field on wire Q. Therefore, due to the absence of the magnetic field, our force will also get reduced to zero. Okay, one second. Due to this wire P, the magnetic field will be inwards on the wire Q. And due to the wire R, the magnetic field will be outwards. Okay, this one inwards and this one outwards. Okay, due to which what happens? Both the fields will cancel each other out. Okay, they will completely cancel each other out. Therefore, there will be no net field. Since there is no net field, what happens? There is no net force because both the fields are zero. The field is becoming zero. Therefore, the force also becomes zero. Okay, so no force will act on Q. Akshay, can you do one small thing? Can you open your answer keys for this chapter? Okay, so that we can also corroborate whether we are correct or not. Okay, yeah, I'll move on to the next question for now. Uh, a long straight wire carries a current of 9 amperes. A square loop of side length 15 centimeters is placed 5 centimeter from the wire. Okay, 15 centimeters is placed 5 centimeter from the wire. There is a clockwise current of 4.5 amperes in the loop. Determine the magnitude and the direction of the magnetic force acting on the loop due to the current in the wire. Okay, so we know the direction of flow of current. Okay, we know the direction of the flow of current. We know how much current is also flowing in this. Now, let us imagine what is happening here. See, here the current is in this direction, both of them are in this direction. Now, but on this side, what is happening? The current, oh, it's like this. One second. So, how do we solve this problem? Okay, so basically, we have to add all the forces that are acting on the four sides of the loop. There are four forces that are acting on the four sides of the loop. We have to understand how they work. Okay, so basically, right now, we are having what? We are having a 15 centimeter sided square, right? It's a 15 centimeter sided square. Now, because of this, what is going to happen? This side will experience a force. What will be the direction of force? Let's see. We know that the magnetic field produced due to the straight wire is practically inwards inside this one, right? So basically, if you place the current direction of current here and the magnetic field inwards, what do you observe? You observe that the force is going to be acted on this direction, right? Okay, now let's look at this one. For this, what is happening? For this one, the current is in this direction, like this. Magnetic field is still inwards. Therefore, the force acting on this side, let's call this A, B, C, D. This will be F, A, B. This will be F, B, C. This will be F, like this call is E. C, F, C, E, and F, nille. And so the current is moving in this direction here, right? Like this. So again, current like this one, magnetic field inwards. Therefore, the force will be acting downwards. So this will become FAD. Okay. Now, for this one, for the CE value. Okay, so CE has the current going like this. Okay, the current is downwards for CE And here also, the current is downwards only. We can consider this to be a single loop. We can consider this to be a single loop because the current is overall downwards only in this direction. So the current is downwards. The magnetic field is here. Therefore, the force will act in this direction. We can call it FCD. So what are the four forces that are acting on the loop? FAB, FBC, FCD, and FAD. We have actually figured out the directions of all the three using our Fleming's left-hand rule. In all this side, all this plane, the magnetic field will be inwards. Okay, the magnetic field will be in the inward direction. Now, the length of BC and AD are the same because it's a square. Okay, the current flowing in the both the sides is also the same. The current flowing through the wire is not going to change for both of them. So these two will have the same forces acting on both the sides. So they will cancel each other out. Okay. So FBC and FAD are basically cancelled. Now, the force, where will this overall wire move? Will it move in the right direction or in the left direction? It will move according to whoever's force is bigger. Okay, we know that the value of force is what? Mu naught I1 I2 upon 2 pi r. So the r is at the bottom. The distance between the two wires is at the bottom. So what does it mean? Force is inversely proportional to the distance between the two wires. Okay, so basically, since the distance between these two is only 5 centimeters, and between this wire and this wire is 20 centimeters, therefore, more force will be acted upon here, less force will be acted upon this side. So AB, the side AB will experience more attractive force, and CD will experience a less repulsive force, due to which what happens? F net will become equal to FAB minus FCD. This will be the net resultant force acting on the wire, and the wire will overall move towards the left hand side. No, no. Why is the force actually being affected? It is, it see, what the theory behind it is we need to understand. Okay, the force is not actually being applied on the current, the flow. It is not affecting the flow. Why is it not affecting the flow? Because it is always perpendicular, right? It's a perpendicular force. So no force is being used to actually move the charge. The force that is being used is to actually move the conductor as a whole in the perpendicular direction. Okay, the force will not be used to increase the current. The current will not change. Okay, why should the current? We have to. Who said we don't? See, Akshay, FAB is what? FAB is equal to mu naught I1 I2. Okay, huh? So I will write it like this: mu naught IAB upon 2 pi r into L. Okay, since we don't know, do we know the value of L? Oh, we do know the value of L. No, it's 15. So FAB is equal to mu naught upon 2 pi is what? 2 into 10 to the power of minus 7. Mu naught upon 2 pi is 2 into 10 to the power minus 7. I1 is how much? 9 into 9 into IAB is how much? 4.5. Because the 4.5 amps is the one that is flowing through the loop, right? Multiplied by what is the length of the conductor? 0.15, that is 15 centimeters upon R is how much? 5 centimeters. That is 0.05. This will be the answer for FAB. Okay, so FCD will not have a very much different answer. 10 to the power minus 7 multiplied by, exactly, No, both of them have 4.5, Akshay. This one also has 4.5. 4.5 is the second conductor. So it will be 4, this into 9 into 4.5 into 0.2 upon 0.05. Okay, clear? So 0.05 multiplied by 3 is 0.15. Okay, 0.05 multiplied by 4 is 0.2. So what is the final answer that you will get? You will get 4.5 into 2 is 9. 9 nines are 81. 81 times 4 is 8. 4 are 32. 3, 2, 4 into 10 to the power of minus 7. Understood? So 324 into 10 to the power of minus 7 for the basically, yeah, for this one. Or you will get 3.24 into 10 to the power of minus 5 newtons per meter. Okay. No, not newtons per meter, just newtons. Just simply newtons. No newtons per meter. Because we have calculated the force, not the force per unit length. And for the above one, what will it be? Oh, I'm so sorry. I'm so sorry. Yeah, you are correct. Yeah. Yeah, no, no, it's fine. You will get 4.5 into, yeah, 0.15 upon 0.2. Okay, so this and this gets cut off. You will get 10. 10 into 1.5 is 1.10 into 0.15 is 1.5. 1.5 into 9s are 13, 13.5. 13.5 into 4.5 is how much? 60.75. Okay, fine. So you will get 60.75 into 10 to the power of minus 7. Okay, or 6.075 into 10 to the power of minus 6. Okay, and for the above one, what will it be? It will be 9 twos are 18, and 4.5 into 3 is how much? 4 3 are 120, 135, 13.5. Okay, so 13.5 into 18 is how much, Akshay? 243 into 10 to the power of minus 7, or simply 24.3 into 10 to the power of minus 6. What is 24.3 minus 6.075? 24.3 minus 6.07. 18.225. 18.225 into 10 to the power of minus 6, or 1.8225 into 10 to the power minus 5. 1.8225 into 10 to the power of minus 5. Clear? Is this answer correct also? Okay, that is fine. So this is how you find the answer. So the overall magnitude is how much? This value. The overall direction is what? It is towards the wire. It is getting attracted towards the wire. Understood? Is there any doubt in this question? Okay, fine. Let's move on. Okay. So measurements, the definition of an ampere. Okay, we are going to understand what an ampere actually is. Uh, okay. Until 2019, the ampere was defined in terms of force between two current carrying wires. Okay, and what was the definition yesterday that I taught you? The definition that I taught you was 1 ampere is defined as the current that flows between two straight conductors having separated by a unit length. Okay, and if the force on the wires is 2 into 10 to the power minus 7 newtons per meter, then the current is called 1 ampere. Okay, so I'll just read as I say it again. If the force acting on two current carrying conductors placed parallelly to each other separated by a distance of 1 meter in vacuum, then if the force experienced by them is 2 into 10 to the power minus 7 newtons, then the newtons per meter, then the current flowing through the conductors is called 1 ampere. Okay, that is the definition of 1 ampere. It's not in your book. Okay, you can write this down. I'll just write it down. Okay, once again, see, 1 ampere. 1 is defined as the current that flows between two long conducting wires placed placed 1 meter apart in vacuum experience a force of 2 into 10 to the power minus 7 newtons per meter. 1 ampere is defined as the current that flows between two parallel long conductors conducting wires placed 1 meters apart in vacuum experience a force of 2 into 10 to the power minus 7 newton per meter. This is the definition of 1 ampere. Okay, let's move on. This was the definition. Now, the old-fashioned definition was that the ampere is a constant current which maintained in two straight parallel conductors of infinite length and negligible cross-sectional area 1 meter apart in vacuum would produce a force between them of 2 pi into 10 to the power minus 7 newtons, 2 pi into 10 to the power minus 7 newtons for every meter of their length. 2 pi, yeah. Pi, yeah. Wait, what? We know that force per unit length is equal to mu naught upon 2 pi r I1 I2. Mu naught into I1 into I2 upon 2 pi r. Therefore, mu naught is value what? 4 pi into 10 to the power minus 7 multiplied by I1 multiplied by I2 upon 2 pi r. This pi and pi gets cut off. This 2 and 2 gets cut off. I1 is 1, I2 is 1, R is 1. No, Akshay, it is 2 into 10 to the power minus 7 only. There is a printing mistake here. This one. It is going to be 2 into 10 to the power minus 7 because the pi in the above and the below gets cut off. Fortunately, students no longer need to learn this. This post 2019 definition of an ampere takes as its starting point the charge of an electron, defined to be 1.6 into 10 to the power minus 19 coulomb. This is also an ampere second. This is also an ampere second because the second is also defined SI unit. This leads to a direct definition of ampere as a coulomb of electrons flowing past a point in 1 second. How many electrons? If 1 coulomb of electrons flows through a small cross-sectional area of a wire in exactly 1 second. Okay, it's like this. If you have a race, in that race, what is happening? If like 10 drivers crossed the finishing line at the same time, then we say that what 10 people have the same position, right? If 10 people, 10 cars crossed the finishing line in the same time, then we say we basically place all of them in the same position. Similarly, okay, in a cross section, if basically 1 coulomb worth of electrons, 1 coulomb worth of electrons were to flow from one place to another, they if they were to cross the finish line, then what would happen? They would produce we would call the definition to be 1 ampere worth of current is flowing through the wire. Okay, so 1 coulomb worth of electrons flowing through a cross sectional area in every 1 second, we call it 1 ampere. Okay, because we know the formula. What is the formula for current? Okay, current is equal to charge upon time. Okay, how much charge is flowing through a conductor and how much time is being taken by the charges to flow through the cross section of the conductor. That is defined as I. Clear? That is what I represents. Next. Because of the second, it is also, wait, this links to the work on electrostatic fields in topic D2, and this explained in more detail in the tools for physics section on page 334. We now have two constants, epsilon naught, the permittivity of free space, and mu naught, okay, the permissibility. Mu naught dot epsilon naught has a unit of Coulomb square Newton inverse meter minus 2, while mu naught has a unit of Newton ampere minus 2. The product of epsilon naught and mu naught, yeah, yeah, epsilon naught is the permittivity. It is the permittivity. Mu naught is the permeability. Exactly. The product of epsilon naught and mu naught has a unit c square upon nm square n upon a square. So basically this n and this n can get cut off. Okay, so you will get c square upon m square a square. Because c upon a, charge divided by area, has a unit of a second, then epsilon naught mu naught has the overall unit of meter square second minus 2, which is 1 upon speed square. Multiplying the knowledge of value of permittivity and permeability for force free space, and the answer 1.1 into 10 raised to the power minus 17, which is 1 upon c square, where c is the speed in a vacuum of an electromagnetic radiation. Simply, all of this is trying to tell you that the mu naught and epsilon naught, if you multiply them, you will get what? C is equal to 1 upon root under mu naught epsilon naught. Okay, or simply mu naught epsilon naught is equal to 1 upon c square. Okay, these are the two values that you get. Clear? Next one. It is going to be used. It will be used somewhere, at some place. Mu multiplied by epsilon naught can also be equal to 1 upon mu naught epsilon naught will always be equal to 1 upon c square. 1 upon root under mu naught epsilon naught. Okay. Now, this result shows the very strong connection between electric and magnetic fields. It arose from Maxwell's equation that are discussed elsewhere in this book, but now treated as a definition of epsilon naught in the most recent version of SI. Okay. Okay. Next. Can we will finish this one, but can we do the charges moving in a uniform magnetic field tomorrow? Uniform electric field? Okay. It is easy to believe that vectors are simply used for physics, scaling diagrams, but this would not be true. Vectors come into their own in mathematical description of magnetic field as well. Okay, so vectors come into their own in the mathematical description of magnetic forces and other parts of the subject. Scalar can also be multiplied together in one way. Run a relay with 4 stages, each of distance 100 meters, and a total distance traveled by the athlete is 400 meters. The product of the two scalars is always going to be a scalar. These are all simple things, right? Scalar multiplied by scalar is always a scalar. Okay, vectors, because of the additional compilation of a direction, can be multiplied together in two ways. You have the scalar product, that is F dot S. Okay, that is work done, and all of these have scalar products. Okay, so basically what happens here, you get something known as a dot product. Okay, and the other one is called a cross product. The vector product, sometimes called a cross product, where two vectors are multiplied together to give a third vector. This is known as A cross B. Okay, so it is a huge topic. Let's do one thing. We will finish this in tomorrow's class. Okay, in tomorrow's class, I will give you a small introduction in scalar multiplication of vector forces and the vector multiplication of forces. Okay, so I know you had a lot of disturbances in today's class. Okay, you are having problems with the internet connection and all. I will upload this video in the YouTube. Okay, you can watch it there if you have any doubts. Okay, read through till here and we'll join in tomorrow's class. We'll continue tomorrow's class. I'll let you know the timings. Okay, I will let you know that. You are again free tomorrow morning, right? Around 10:30. No problem. No problem. No problem. No problem. No problem. Okay. Okay. So, hello students. I hope you enjoyed my video. I am trying my best to explain these concepts as simple as possible. Okay. If you really like my video, please do like, share, and subscribe. And I'll meet you in the next class. Thank you.